A talk by Mike Tehranchi from Cambridge, who will speak on hedging with variance swaps.
Well, thank you very much for the introduction, and it's an honor to be asked to speak here. And I will hopefully, I'm going to tell you about some of the things I've been interested in the past couple of years, and hopefully you'll find it interesting also. This work, the only parts where I claim that there's actually a theorem proved was done by a PhD student at Cambridge named Francois Barrier, who actually now works for Nomura. He works in the Lehman Brothers building, because Nomura Securities bought Lehman Brothers last year. Okay, so I suppose that many of you were here last week and saw Professor Zabchek's talk, so I don't have to explain the very fundamentals, but the idea in mathematical finance is that you have a model for prices, and the model, since we're probabilist, will be a stochastic process, and it's defined on some fixed probability space. It's n-dimensional, let's say, and the crucial idea is that for this model to be good in the economical sense, that there exists no arbitrage opportunities, more or less it means that there exists a measure that's equivalent to the original measure, or locally equivalent, or something, so that the prices are martingales or local martingales or sigma martingales. But essentially the fundamental theorem says this economical this economical concept of no arbitrage is more or less equivalent to this mathematical concept of the existence of an equivalent martingale measure. And so for discussions of pricing and hedging and that kind of question, it's in fact enough to throw out the measure P and work directly with this measure Q, which is this martingale measure. And this was the approach taken last week, and it's essentially the approach we'll take today too. And just for those who are not so familiar with mathematical finance, there's several ways of approaching this problem of constructing price processes that satisfy this this no arbitrage condition, the existence of an equivalent martingale measure. So the classical approach, which was a Nobel Prize winning idea of Black and Scholes, Merton, was to pick out some of the assets as fundamental assets and don't try to explore why they have a certain price. You just model their prices as a stochastic process. So they have some. This is something that you maybe can infer from statistics, that the price of a stock is a geometric Brownian motion, say. That's the classical example. Though, of course, that is not such a good, statistics don't actually fit that assumption, but one could, in principle, test that assumption. Okay, so you have the fundamental assets like stocks, say, and then the rest of the assets in the market are derivative assets or contingent claims. So their prices their payouts will depend on the realizations of the more fundamental assets. So what one can do in this case is take the fundamental assets, and since we're not really trying to pretend that we understand where the prices come from, we're just going to say they're martingales or local martingales on this fixed probability space. And that way we ensure that at least the first D part of the market has no arbitrage. Now for the contingent claims, normally they're going to be some functional of the price processes of the fundamentals, and so the payout, of course these are European style contingent claims, so there's a fixed date of maturity, say TI, so the ith claim matures at time TI, and its payout will be given by some functional of the price process. And if we define the prices of the contingent claim at earlier times to be given by this conditional expectation, then we know for a fact that the C's will be martingales also. So therefore, we've taken care of both parts of the market. The fundamentals, we just assumed they were martingales. We model them as such. And then the rest, we define them to be define the prices by this formula, and then, that formula guarantees they're martingales. So therefore, we have all the prices in the market are now martingales, no arbitrage, and we have a at least we have satisfied that economical constraint that our prices don't have any free lunch, no riskless profit is available in this market model. Okay, so there's this is a widely used methodology, and it's principled. Sorry.
How comes of course assume martingale, but then you have function for martingale. That's not necessarily martingale.
Yeah, so this is some fixed random variable C subscript ti,
Yeah.
and that's defined as this functional of the path of the martingale, S.
But the second line, when you define it using terminal value, that thing is not martingale anymore.
Well, it's martingale with respect to this filtration. So this F is denoting the, so in the background I have this filtered probability space. And
Oh yeah, when you defined it is, but before you defined it, it wasn't martingale, right? It's just
yeah, so this is just a random variable, the top expression,
okay.
for it's this the payout of the contingent claim labeled I, and its payout happens at time ti.
Okay.
And then now I'm just giving all its earlier prices just by conditioning the terminal price
It's okay.
by this filtration.
Yeah, I thought you defined time t as a value for st as well.
Okay. Thank you. Sorry that wasn't more clear. Okay, so a problem with this approach is that, well, we start off with the fundamental prices, which are our underlying assets like the stocks, and we model them just as martingales. So there's, well, lots of martingales in the world to choose from, say geometric Brownian motion, or the Heston model, or Sabre model, or whatever, and these models all have parameters in them. So, but okay, so you have your family, and you know that whatever family you choose, you'll have no arbitrage. And then you price the contingent claims by this formula, and again, because this formula ensures that the prices are martingales, there'll be no arbitrage. So we'll have prices of contingent claims that depend on these parameters theta that are parameterizing the family of models of the underlying. And then, well, in a liquid market, let's say call options, we don't actually need to use the Black-Scholes formula to price call options or whatever formula you want to use because, well, they're so liquidly traded that you can just go to Yahoo and type in, what's the price of this call option, and a price is quoted because they're so liquid. So then you try to choose the theta from your model of your martingale to match the price that you actually see. So you have this inverse problem. But of course, it's not possible because your set of parameters will be smaller than the set of prices that you can observe. You won't be able to match every price exactly by this methodology. So somehow you believe that some of the prices are wrong, in a sense, because otherwise, how could your model disagree with the prices you see observed? So you're thinking that the prices of the underlyings are somehow really true, and the prices of the contingent claims are somehow not really true because your model will produce one price and yet you observe another price, even if you try to pick the theta that matches it as closely as possible. Okay, but so there's this calibration problem. Another approach which doesn't get rid of the calibration problem, but it pushes it into the background a bit, is called the market model approach, and usually the names of Heath, Jarrett, and Morton are attributed to this idea. Of course, a lot of people have worked on it since. This was probably 89, I guess, with Morton's thesis. Well, the idea is that you model all the prices simultaneously as a martingale or as a local martingale. So you don't make a division between some assets being fundamental and some assets being contingent. You just model all of them. And of course, you have to check consistency because some of like with a call option or a bond, there are certain things that have to happen at the termination of the contract. For instance, a zero coupon bond, if we're talking about, say, a treasury bond as opposed to a mortgage-backed security or something, really ought to pay its 1 unit of money at terminal. So there has to be some consistency check. And the way that this often is done is by a reparameterization of the prices. So rather than modeling the prices directly, we model some reparameterization of the prices, and then we make sure that the prices are martingales by usually a drift condition. Okay, so again, I'm going slowly for those who know this, but hopefully for those who don't, this will clarify the arguments. So an example of the classical martingale type approach for the bond markets would be to, say, model the spot interest rate, the short interest rate. The Vazicek model, which is just modeling R as an Ornstein-Uhlenbeck process, or the Coxinger-Saul-Ross model, which is to model R as a square root diffusion. Okay, so you take some model, whatever you like, as for R, and then you define the bond prices by this formula. And this formula guarantees that the discounted bond prices are martingales. So you know that we have no arbitrage in this bond market. Okay, so well, what's left to say? Well, we can bond prices are not so informative. So what I mean by that is that typically, if you plot the price of a bond against its maturity, well, the longer you have to wait to get your money, the less you're willing to pay for it. So bond prices are not so informative, but taking the minus the logarithmic derivative somehow gives you the instantaneous forward rate. So essentially a market expectation of the future spot rate. But however you want to think about it, you can just define it as this. And what you see is, because of these two formulas, assuming a sufficient regularity of the process R, then the short rate is given by the left-hand endpoint of the forward rate curve. Okay, so that's the martingale approach. But you can turn this approach on its head. And this was proposed by Heath-Jarrow and Morton. And you first start off with a two-parameter stochastic process, F, and you assume it evolves according to this particular SDE. It's an infinite number of SDEs parameterized by capital T. One can even reparameterize this to get the Musela PDE, SPDE, which was spoken about last week. But just to keep things simple, you assume that we have this random field and it evolves in this fashion. And now we define this stochastic process R by setting R of t to be f of t and t. And we define this process P to be such that P of t comma capital T is given by this exponential. Then, well, by Ito's formula, you can check that this quantity here is a local martingale. So therefore, it's actually a pretty good model for the bond prices. Or at least it's pretty good in the sense that there's no arbitrage. Yes?
So in fact, you said that somehow, in relation with the no arbitrage, you said the local martingale, or single martingale is almost the same. But in fact, isn't it important, in fact, to know if you have a real martingale instead of a local martingale?
Well, yes, it does have some consequences, but it's not at the level of arbitrage. It's the level at other. For instance, when you're in continuous time, you have to worry about admissibility. So that's right. So local martingales, there's no way to make arbitrage from a local martingale, even if you want to use this admissibility criteria that you can't go arbitrarily far into debt. So so it may be unrealistic. Well, I mean, to give you an example, if you may know this example, but I mean, you must know this paper of Cox and Hobson about strictly local martingales. Yeah, okay. I mean, there are some strange things that happen. So this is a kind of a digression from this, but oh, can you see me? Perhaps for instance, suppose that you had a stock process that started that has an evolution according to this SDE. So this is the reciprocal of a three-dimensional vessel process. So this is completely well understood. In particular, it's a strictly local martingale. So so the expected value of S capital T will be strictly smaller than S naught. On the other hand, since this would be this model would be complete, there exists a portfolio pi t and an initial wealth x smaller than S naught. Oops. Such that x plus integral from 0 to t pi t dst is equal to S capital T. Okay, so what this is saying is that if you have this market model for your stock, there's no arbitrage because it's a local martingale. On the other hand, there exists a strategy and an initial wealth that's strictly smaller than the initial stock price, such that you can replicate the stock price at some future time with less money than it costs just to buy the stock now. So, and you're only trading in the stock itself. So, I mean, it seems kind of weird that such a thing is possible, but there's no arbitrage, right? I mean, this seems counterintuitive because you would think that how could you could replicate the stock with less money than it costs to buy the stock? It doesn't make sense. But if you think about what the arbitrage would be to buy this this portfolio and sell the stock. But the problem is then your wealth would go arbitrarily negative, and so you wouldn't. It's not really an arbitrage if you use the definition of an arbitrage of your admissible strategy is that your wealth is bounded from below. So there are some peculiarities that I'm just going to gloss over altogether.
The class of admissible strategy has to be reconsidered.
That's right. Yes. Yeah. So absolutely. So there are some strange things when you have strictly local martingales that kind of make the theory less clean, unfortunately.
In real life, everything is discrete, and there's no difference between local martingale and martingale.
That's right. In fact, in real life, everything's bounded. Right?
Yeah.
You can't have a stock worth more than $30 trillion, say. so everything. Yeah. So yeah, these are for mathematicians, not for.
Yeah, no, but strictly
The
local
bonuses
martingale
are
is
unbounded.
Yeah.
You don't have any bound on bonuses.
Okay, but yeah, so this is a digression from the. But for those who are interested, so at least if you pick this one definition of admissible, this would be an admissible. I mean, this would be a no arbitrage market model, and you could be happy, even if the economists would say that's not realistic. Okay, so what the advantage of this HJM framework is that notice this random field, it's this evolution equation, as I said, for every capital T, we can evolve this random field. We can choose the initial forward curve as our initial condition to this evolution equation. Right, so So the evolution's in little t, and so I just pick a f0 comma capital T for every capital T. So somehow I can actually match every single bond price exactly at time 0. So that's different than the case where I had considered the bond as a contingent claim, and then I had to fix a parameter to somehow match the bond prices as well as possible by having fixing the parameter inside the short rate model, say, because I can really match every single bond. But of course, this really is just, it's cheating something. I'm pushing this calibration problem to the next step. Now I want to now use a HJM model to price a swaption or what have you. But in fact, those are pretty liquid, so then I can use the quoted swaption prices to pick the volatility, because you notice that no matter what sigma I choose here, as long as everything makes sense mathematically, then this will be a local martingale. So there's no arbitrage, and I exactly match all the bond prices. So I can pick anything for sigma, and that seems pretty strange that you have so much flexibility for sigma. And in fact, you don't, because you need to, of course, on one hand, match the statistics, the statistical evolution of the equation, and then also you probably want to match liquid interest rate derivatives. But at least you have a family of contingent claims that you can price exactly, because it's the model input. Okay, now that was interest rates. Now I'm going to switch gears a bit and talk about variance swaps, which are very similar in a lot of ways. A variance swap is a contract that pays. All right, so you take the log of the daily, the ratio of the prices from one day to the next, and then you square it, and then you sum it up. So I think it's pretty funny. It's a payout for a contingent claim. So if you had, if you were trying to explain to your friends back home what a call option is, I think many of you probably know what a call option is, but just to recap, it's the right but not the obligation to buy a stock at some fixed time in the future, at a fixed price that you agree upon now. I think you can explain that in ordinary language. But why on earth would you be trading a contract that has this payout? There's these legal documents that say you take the, you have to specify in the legal document the base of the logarithm, obviously, which is kind of strange to that. But, and it's clear that's because they're mathematically minded people who work in banks that they cooked up these things. And of course, this is related. If you take the limit, S is a continuous, positive continuous semi-martingale, then it'll be its quadratic variation. So that's of course where it comes from. But
so in the limit, one gets a quadratic variation.
Yes, that's well. So that's why these things were proposed as traded instruments. But it's not something that one, I think, would have cooked up from first principle. From financial first principle, I think. But anyway, they exist. So there you have it. Okay, so if you prefer a nice formula rather than messy ones, we throw away the expression on the left, which is the real contract, and we'll move to the expression on the right, which is what we all define as the payout of the contract. So then the martingale approach to pricing one of these things is somehow model your underlying price S by however you like, as long as it's positive and a local martingale, say, and then you can compute the price of the variant swap by this formula, and that would guarantee that now this price, once we introduce it to the market, the augmented market with the stock and the variant swaps, is again arbitrage free. For instance, we could take S to be geometric Brownian motion, and then of course the variant swaps would just be the volatility of the geometric Brownian motion squared times the length of time till maturity.
You don't assume the stock price is continuous for the period.
Yes, so I'm going to assume it is. Yes, yeah, that's a good point. I should say that a positive continuous martingale, so that this approximation corresponds. Yes, thank you. That's right. I should have put that on the slide. Yes, so everything's continuous in this talk. So this approximation leads to this approximation. Okay, and then we can define the forward variance just by the derivative as with respect to capital T. Again, if you think about it, on the one hand, as a function of capital T, variance swap prices ought to be increasing. So if you just see an increasing curve, it is less informative than the derivative of that increasing. So that gives you kind of locally how much the market expectation of future spot volatility would be. And so let's just define this quantity to be like this. And of course, what happens if you write your stock price process in this form, so it's a exponential martingale with the integrand of the Brownian motion being sigma, then the spot forward variance will exactly match the spot squared volatility. I mean, again, subject to checking all the details for this convergence. But this is just the analogous statement to saying that the spot forward rate is equal to the spot, the left-hand endpoint of the forward rate curve is equal to the spot interest rate. So it's the same kind of statement. So it's one of these consistency checks. Now, we want to redo our HJM discussion. So we turn that on its head, and this was proposed by Hans Buehler a couple years ago. And in this case, it's much simpler than HJM. You take your initial variance, forward variance curve is given, and then you evolve it. Well, actually, in this case, all you have to do is evolve it as a parameterized family of martingales, of positive martingales. So that would be the HJM equation for forward variances. So, in other words, it's not so impressive, but we need to define a spot volatility, so we have to make sure that this curve stays positive, so that we can set sigma to be essentially the root of the left-hand endpoint of the curve times some unit vector. And now, since we have sigma, we can define a stock price to be given by this Dolian exponential of sigma dw. And so therefore we have our variance swaps, our variance forward variances are martingales. Our stock price is a martingale, so therefore we're sure that there's no arbitrage, and then we can actually recover our variance swap prices by just integrating up the variance up to today, and then just the forward variance between today and the maturity case. Okay, so that would be the market approach. You take the market prices of forward variances as your input, and then you reconstruct a compatible family of prices, and then you actually model your stock price not as the fundamental, but actually almost a derived quantity, because its deriving volatility process is just coming out of some the left-hand endpoint of this forward variance curve. Okay. So the point of this talk is to talk about hedging. So the hedging problem would be to start off with some, say, a contingent claim that matures at some future time, capital T. So it's just a script f t measurable random variable. And then we'd like to replicate it in the sense that we write it as stochastic integral with respect to a portfolio process, which we'll think of pi as the number of shares that you have to hold between now and capital T, shares in the stock, and then psi are the number of variance swaps you ought to hold. Okay, so this is the problem I'd like to think about now is, given a contingent claim, C, is it possible to say something interesting about these pi's and psi's? Do they exist? How do they depend on C, for instance? This is see if the Brownian motion that's driving all the dynamics is finite dimensional, and the filtration is generated by this Brownian motion. So we have this Martingale representation theorem that says that the left-hand endpoint, the left-hand side of this equation can be written as a stochastic integral with respect to this finite dimensional Brownian motion. But the right-hand side can also be written as a stochastic integral with respect to that finite dimensional Brownian motion. For any choice of maturity dates for our forward variances.
So the TE, the small TE are all bigger than capital T?
They don't really matter. I mean, we can define the curve to, like Professor Zabchek's talk, the curve dies after. Right, so you set the evolution to be 0 after the maturity date. Yes, thank you. I guess I should be more clear. But it doesn't. I mean, I guess this expression doesn't really make sense economically unless S is smaller than TI, so then you'd want to turn off the size. But you can do that by turning off the dV after maturity by setting the evolution to equal to 0. I mean, to be constant after that. Okay. So as I said, that given any choice of maturities, and if we had a finite dimensional Brownian motion, then more or less generically, you'd be able to solve for this finite dimensional set of equations, because on the left-hand side you would have Martingale representation theorem, something alpha dW, and then you have again something here that's going to be something dW, and you have the unknowns pi and psi i's, and given enough of the TI's, you would have you could invert this matrix equation and come up with a portfolio. So in particular, the trading instruments, the claims, the forward variances, the choice that you pick wouldn't depend on the claim that you're trying to hedge. Okay, so you could say that's not a problem, and maybe it's not a problem, but it seems a bit strange that if you had a look-back option that's maturing in 1 year, to use a forward variance from 5 years as in one of your hedging instruments. Somehow you would have, so it seems that that instrument won't be perfectly correlated in some kind of vague sense with what's happening between now and 1 year, because there's kind of extra information that's happening 5 years from now. Even though it's measurable with respect to now, it just seems that the evolution should somehow incorporate the fact that the market participants have to think about future events in order to price the more distantly maturing forward variances. So if in a finite dimensional noise situation, you would lose any sense of maturity-specific risk. So that's why one could argue that a way to get around this would be to introduce infinite dimensional noise.
But your V, this with the variance swap, they are dependent on the maturity, and they're random by SPDE. The V itself depends on the TIs.
Yes, that's right.
And that's random. So
yeah.
For me, that depends on the maturity.
Right. So the actual the number of shares that you would hold would depend on the TIs. But the point I'm trying to make is that the label, which TI you would pick, doesn't matter if you have a finite dimensional noise. So for instance, I could pick right now TI to be 27 years, 28 years, and 38 years. And then I want to replicate a contingent claim that matures in 1 year. If we have a three-dimensional Brownian motion, I could be able to solve these equations for the coefficient in front of the DWs to get the replication. And somehow, of course, that inversion to solve these equations is going to depend on the dynamics of the 27, 28, and 30-year forward variance. But yeah, I would have perfect replication with with variance swaps, which I think probably shouldn't be able to perfectly replicate something. And that's one would think that you might want to use variance swaps with shorter maturities that somehow capture. Their dynamics would somehow more closely correlated to the dynamics of something that's shorter maturity. But in this framework, there's nothing that prohibits it. You would have perfect replication if you can just invert this matrix. So somehow you can choose the trading instruments before you know what you're trying to hedge. And that seems strange, but it could be the case that if you have a very small dimensional noise, then you should. The market's too complete. It's very redundant. There's a lot of assets that are just replicating. That are redundant. Like the forward variances are all. You could throw out most of them and get the same exposure to a particular Brownian source by picking just a fewer. But since there are lots of them, and we want to somehow have a notion of maturity-specific risk, that's why we'll talk about the case when you have an infinite dimensional noise. Okay, so this kind this story might sound familiar for those people who know the interest rate literature, and so the first kind of papers that were discussing bond portfolios are now 13 years old. That's depressing, but there you have it. And so, but over the years, people have thought about it, including me. That's why I put the slide up. So there's some various issues about what the portfolios look like, whether or not there exist portfolios at all. In particular, when you have an infinite dimensional noise, even if this infinite dimensional Wiener process generates the filtration, so we have so there's exists a unique equivalent martingale measure. It still may be the case that the market is incomplete in this rather technical sense that, which I guess I have a slide that might explain. So, so there is this technical problem that occurs when you have an infinite dimensional space. But to explain the framework that I consider this problem in is essentially this Dobroto-Zabchek evolution equation in a infinite dimensional space framework rather than SPD kind of framework. But you have you pick a function space to be where all of the forward variance curves are living, say. So F to be easy mathematically should be real, should be separable. The Hilbert space helps, so you have Ito's isometry. Having continuous functions is nice, so that you can talk about point evaluation. And then we're going to suppose that our forward variance curves live in this function space. So for every little t and every omega, we have a curve that's going to be in this fixed, non-random function space F. And so a pretty convenient space would be a weighted Sobolev space, so that you know that say point evaluations exist. There's even the limit at infinity exists. Integrals are bounded functionals. But so these are coming from mathematical convenience reasons, not necessarily from financial considerations. Okay, now since F is going to be an infinite dimensional space usually, to avoid this kind of degeneracies that I was talking about before, we're going to assume that our Brownian motion is also interdimensional. So you don't have to specify what space it lives in. You could think of it as a list of Brownian motions. You could think of it as a cylindrical Brownian motion in some separable Hilbert space, which of course those two ideas would be the same if you chose that separable Hilbert space to be little L2, which for the sake of presentation I will do, but I mean, you can just think of it as either as a list of Brownian motions, a countable family, or as somehow a cylindrical Brownian motion on a Hilbert space. And so now that we're in this function space setup, we need to talk about the volatility of these forward variances, excuse me. So a sigma is going to be now a random Hilbert-Schmidt operator. So for every little t and every omega, I get a Hilbert-Schmidt operator from the G, this kind of the space where the Brownian motion is cylindrically defined, and F, the space where I want to have my variance swap curve, or my forward variance curve. And then I assume that this is finite so that I have a bona fide F value martingale my stochastic integral. Okay, and now that I have this thing valued in F, where I've chosen F to be smooth enough that point evaluation makes sense, so I can now evaluate V at a point, take the square root, and lambda is going to now be taking values in G, or the dual of G if you want to get really technical. And we can now define our stock price by this process. So the ingredients are this Hilbert-Schmidt valued process sigma and this random variable lambda, or this predictable process lambda. And that completely determines the model. And in the sense that we know once I have specified those two processes, I then construct my forward variances by stochastic integration, and then I then take the evaluation at a particular point, take the square root, multiply by lambda, and then define the stock prices, again, another stochastic integration. But in this way, I know there's no arbitrage because there's a martingale here, and there's well, at least a local martingale here. Okay, so that's the kind of the function space way of saying what I had said before. And again, if you want to think about portfolios, will be, they make the most sense if you think of them as ordered pairs of the number of shares you hold, which is a real number, and then the number of forward variances you hold. And so remember, the forward variances are valued in as space F, so the portfolios ought to be essentially elements of the dual space. Right? If we look back at this expression, so this would be evaluating the forward variance curve at a certain number of points. So essentially taking the portfolios to be Dirac deltas. But the generalization would then be to let our portfolios and the forward variances just be elements of F star. And since we've made sure that, again, F was smooth and the delta measures are in F star, so classical trading strategies are special cases. And we can, again, rewrite everything in terms of this cylindrical Brownian motion. So we can interpret the left-hand side by this stochastic integral on the right-hand side, which is well defined. Okay, so now getting back to the point of approximate completeness. Well, if we did this argument that I was making before, we want to have this quantity on the right equal to the stochastic to some random variable xc. Then we can use the martingale representation theorem again on xc, and we have that it can be written as a stochastic integral with respect to the cylindrical Brownian motion. And to solve for pi and psi, we just need to, well, essentially solve the system of equations. But since sigma is a compact operator, we can't invert it. So we, in general, can't claim that in this framework we can exactly replicate every contingent claim. So that is why I had mentioned that there was some issues about completeness. Of course, there's approximate completeness. You could have convergent families of trading strategies that can replicate things, but the trading strategies wouldn't converge at F star. They would, but the stochastic intervals would converge to psi. So that's a technicality that I would like to avoid. So I'm going to talk about. Sorry?
Could you classify the replicable?
One, classify the replicable claims. I think that's doable, but I can't tell you what the answer is off the top of my head. Taflin has a paper about this issue for the interest rate case. And, well, as you'll see, what the strategy will employ to actually get a hold of what kind of contingent claims, to say something about the portfolio, we'll use Clark-Cohn formula. So, so then, if we can say the contingent claim is in the domain of the nonlinear derivative, and that all these things make sense, then at least it's possibly replicable, but I'm not sure about the necessity of that. So, yeah, I guess I could point you to the reference if you're interested after the talk. Okay, so now for just the last couple minutes, we'll just say some things that are hopefully relatively new. The idea is to let's, rather than take such a general case, let's take sigma to be Markovian. So we can. Excuse me. The process is Markovian. So we take sigma to be a deterministic function of the this variance swap curve, or the forward variance curve. Again, I have to introduce a little bit of notation. F plus is the set of curves that are non-negative everywhere, because, again, we need to take the square root at some stage. So it doesn't make sense for the forward variances to go negative. Let's see, I'm going to assume that sigma is globally Lipschitz, which probably excludes most of the popular models, but at least one can prove a theorem. And let's see, a condition like this ensures that the forward variances actually stay positive, because you can then dominate it by a stochastic exponential. And I think just for simplicity, just to pick this lambda to be a constant element of this dual space G star. So I won't have to think about the extra bit of randomness that's coming out of lambda, though it can be dealt with if you assume it's, again, a function of v. Okay, so this is the particular setup. And so if g is our payoff function, let's say it depends on a finite number of the prices of the underlying stock at n different times, and suppose it's Lipschitz, so that I can use the Clark-Cohn formula. Then I can show that there actually does exist a replicating strategy, and furthermore, it's unique if lambda and sigma are related by these kind of non-degeneracy conditions. So the point of uniqueness is that it gets rid of these strange replicating strategies that I had mentioned before, that you could replicate a look-back option that matures in 1 year with a 30-year variance swap. Somehow you'd want to think that the variance swap shouldn't be so perfectly correlated with the 1 year look back that it can be used as a hedging instrument. So in this framework, these conditions assure that there's at least unique hedging. But if we want to actually have maturity-specific risk, then you have to make an assumption about how the volatility operator mixes up maturities, and it's maybe not a nice way of looking at it, but it's just saying that the volatility doesn't change if the forward curve is, so if you have two forward curves that are agree on some interval t to u, then when you test the volatility at the time u, then you would get the same volatility. Okay, so if you have a volatility that doesn't mix up the maturities in this particular way, then our portfolio psi, which we are elements of this dual space F star, so their distribution, so we can think about their support, and it turns out the support of this distribution really is between today and the maturity of the option. So that does mean that we have this maturity specific risk after all. So that I mean, so we've traded one problem for the technicalities involved in having infinite dimensional stochastic analysis, but well, I guess that's life. And yeah, I guess this probably is not necessary, but as I said before, you represent the payout of your contingent claim by a Clark-Cone formula, and then you define a tangent process, which is essentially this the derivative of the variance curve with respect to its initial condition, and it has a particular well, operator valued SDE, and then you get a condition that relates this tangent process and the current volatility with the Malevin derivative. So this is classical. In the infinite dimensions, you have to be a little more careful because y is, well, it doesn't exist as a bounded operator generally. So it exists in the, as a strong operator that it's, this doesn't really make sense as bounded operators on, not taking values in LF, but if you test it by an element of F, then you have something that evolves in F, and then, okay, so that's...
How is this process related to Clark-Cone?
Oh, well, because I want to express...
So this is Malevin derivative.
Yes. That's right, yeah. So I have this Malevin derivative here. Xc now is a function, say, of the stock price, and the stock price, the evolution of the stock price is the integral of the forward variance dw. So then, we can see that you can pass the problem from representing the derivative of the payout to the representing the derivative of the stock price, which then goes to the representing the derivative of the forward variance itself, and the forward variance derivative then will be given by this formula, which is kind of the classical formula, just in infinite dimensions. And that is my last slide, so I guess it's a good place to stop. Thank you very much.
Thank you very much. Are there some questions? The subject is not very easy, and you have a specialist field. Maybe after the lecture. The Clark-Cone result was formulated first for finite dimensional case.
Yes.
But everything goes through.
Yes, it does. So
the best source would be, say, for infinite dimensional version of Clark-Cone.
Well, we have proof in this paper with Renee in the analytical applied probability for this case where we have the Hilbert space value processes. So, assuming that proof is correct, it should should work.
Yes?
I think there is a proof of Clark-Cone formula by Van Yerven even in Banach space.
So Wiener process is.
Yes.
I think, do you need the Banach space to be
There are
UMD?
some other problems.
Yeah, because you need to have some control, but I think in Hilbert space it's no problem.
So, some more questions? So, thank you again.